at Arlington, Texas, USA, followed by PhD in Applied Physics, again from the mentioned University of USA. Sir has done postdoctoral training in Advanced Retinal Imaging Alliance and Biophysics and Physiology. He has he has a broad experience in the field of research and development. Sir has a vast list of peer-reviewed research publications. Sir has written a book chapter for outstanding performance in classroom and laboratory. Many awards have been given to Sir. So, on behalf of Principal Sir Govt College Manawar and Department of Physics, I welcome Dr. Kamal Raj Dhakal Sir and all dignitaries and participants. In the last, my special thanks to Dr. Jitendra Solanki Sir for giving me an opportunity to read the profile of Dr. Kamal Raj Dhakal Sir. Thank you so much everyone for listening me. Thanks a lot.
Thank you, Professor Barmanji.
Thank you, sir.
Okay, now I invite our VD Srivastav sir for this program.
Hello.
So,
Hello.
yes, sir. Yes, sir.
Am I audible?
Yes, sir.
Yes. So thank you, Dr. Jitendra Solanki, sir, convener the International Symposium on Modern Trends in Physics and Biophotonics 2020 and Faculty Development Program for the new inducted faculty, organized by the Indian Association of Physics Teachers. So first, I must say something about the Indian Association of Physics Teachers. The Indian Association of Physics Teachers was established in year 1984 with active support from some physics teachers throughout the India, with the aim of upgrading the quality of physics teaching and physics teachers at all the levels, from very preliminary to the research level. Then the Department of Physics, Government College Manawar, District Dhar, India, and the Internal Quality Assurance Cell IQAC. So I welcome Dr. Dhakal, scientist, R&D, AB, Elegant Eye Care, California, USA. His topic is restoring vision of the blind, optogenetics. Actually, it's a very new topic for all of us, where the genetics and opto, these two things mix, and the devices will be very useful for the blind person. So mostly the electronics part, the opto part, and the genetic nervous system part is there. So devices now available and proposed to aid the low vision and blind community, and the algorithm helpful for the visual aids, the augmentation, restoration, the optical and electronic magnifiers, digital cameras, video goggles, all the things which will be useful for the blind. So it is, we are very lucky to know and listen the new techniques of the optogenetics by Dr. Kamal Dhakal. He is the scientist in Algier Eye Care, California, USA. So I invite Dr. Kamal Dhakal for deliver a lecture, Restoring Vision to the Blind, Optogenetics.
All right. So can I start now?
Yes.
Yeah. Principal
Alright.
sir. Yeah, just 1 minute. Principal sir. प्रिंसिपल सर आपको आवाज आ रही है मेरी? think there is some technical maybe issue, or you can start. We will ask him later. We will call him later.
All right. Okay. Thank you, everyone, especially Dr. Jitendra and Professor Burman and Professor Srivastav that giving my nice introduction ahead. And I really like to say hi to everyone, especially student and faculty member of this government college. And I believe some of my friends are also joining. And just to correct, I'm right now earlier I was working with Allergan Eye Care. Right now the AbbVie bought it and we became a single company, and AbbVie is now fourth largest company in the world. And because I'm working on company, I won't discuss anything. Right now I am working due to the company rules and regulations, but I'll be talking all my research throughout PhD and my past postdoc. And so well, wait, it's not. Okay, there is a slightly lag. Okay, very good.
We can see.
So how I really outlined this my talk as to include most of my basic of neuroscience and giving up some idea about vision science and how we can restore, rather going to very deep to the one particular topic. I believe I really like to encourage those students who are from the physics or engineering background and like to jump to this interdisciplinary science, because when I was a physics student, most of the students will hate that biophysics, thinking this is a biology. But I like to tell you this biology is really not only a biology. There is more physics here, more engineering here, and honestly, it's more fun than the real physics. So the first, I'll just give you a general introduction of neuroscience, including optogenetics and some laser delivery. Later, I'll more focus on vision science and how we can really restore the vision that people has lost. It means, can you really restore the vision to the blind person? Okay. This PowerPoint has really issue.
It's not working.
Do I have to?
Yeah, you can just reshare. Okay.
Okay.
That is working.
Sometimes it works. Sometimes I don't know why. Okay.
Yeah.
And so to start with, let me take it out this. So as you see, this is the whole picture of the brain. As we all know, brain is really a commander of in chief. Whatever we do, whatever we think, everything is controlled by that tiny. I will not say tiny, but this is a almost 3 pound of mass, the brain. And this part, really, that every part has its own important function, and nobody knows really till now how this brain works in a whole sense. People are still trying to understand. And if we look at the horizontal, or like this cross section through the eye, it looks like this. So if you later of my talk, I'll just mostly focus on this visual section, but just give an idea of neuro, like the brain, how that visual system works. If you take a cross section, as you see, this is our eye, and if you look at anything in front of eye, this eye has really complicated phenomena, like the left visual side, right visual side, and each part from the object falls to the eye and goes to the um, back of the brain, which is called visual cortex, where everything will be combined, and that we see the things, what we call perception. So if you carefully look at here, from the left visual side, the rays of light fall to the half part of the one eye and the half part of the other eye, and these two halves combine to the one side, and the nasal side, what we call to the nose, this nasal side of the two opposite eye falls to the another side. This is really interesting things. And then when the signal goes, it crosses to the optical chiasm, what we call optical chiasm. And this, so the signal from the two eye is split into four channels, and they really combine at the back of the eye so beautifully. then I'll discuss later. So this is an overview of our visual system. If we think how complex this visual system is, this is the GTI diffusion tensor matrix of the brain. Since 2010, big project like human genome project, human connectome project, and then there is a similar brain initiative project in Europe and America. They invest billions of dollars to really understand the physical connection of brain. We so far don't know anything about function. If we know how the brain, those billions of neurons, by the way, if you are wondering how many neurons in the brain are, there are above 90 billion neurons are connected to each other in such a complicated manner that we think we human. And one of the famous scientists once upon he said, if the human's brain were so simple that we could understand, we will be also so simple that we couldn't. So that's the complexity of brains that gives us that we understand everything. Otherwise, we will be simple animals. If we now cross section the brain, that is small, that visual pathways what I showed you, as you see, these are the neurons, these cortical fiber, and the color represents the direction. You can see these neurons are connected in such a different direction to work a combined work. It looks like a busy map of the New York City, seamlessly working together without any lockdown, without any traffic jam. So that's beautifully our brain works. Even if you further zoom, if you like to see a small part, look at how complicated and how miracle, how beautiful this brain. This is just the recent images from the Human Connectome project that shows the complexity of the structure. Yet we are far away from the function. We know bulk of the function, but that is just a bulk. We don't know detail yet. If you further look at within the 200 micron, this is real image. This is not even computational method. This is the cortical neuron of mice. You can see within the 200 micron how many neurons are interconnected in such a complicated way. So we really need engineering, physics, so many, all those technology, the newest technology, we need to understand the neuroscience or the brain. So those students, if you are a student here, please don't think neuroscience or biophysics is just the biology, anatomy, and physiology. That is part of doctor. We scientists work, we apply here, all those signal processing, your engineering, everything apply. So this is the overall of complexity of brain. You might be wondering now, I know how wonderful our human system is. So, and those students, if you are interested, there is a website, I put it over here. I also share my presentation with Dr. Jitendra. You can get it from here. These two websites, this is the website gives you an idea about how this diffusion tensor matrix imaging works. They have wonderful images. And this is a brain too. This is a Python simulation of all these neuroscience, you can simulate neurons, ganglion cell, any nerve, any part of the nervous system or our body, usually neuroscience. You can use this link and learn how you can computationally using Python or mathematical equation, you can simulate this function. Those for a student. And if you really like to see now, let's see a single neuron. This is the neuron I took it during my grad time using phase contrast microscopy. As you see, there is a bright, usually these are the cultural neuron from the mice in the dish, and they are low contrast. That's why I use a phase contrast microscopy. And if you look at carefully, this is a dendrite, what we call. So they have so many, like this, we call philopodia. These are constantly moving, constantly changing. They are constantly sensing something. And this part, I call them analog. They sense everything. And when they combine the masses, they send the signal in terms of action potential, what we call digital part. Like this either 0 or 1 types of message goes to the brain. So all these neuroscience, this complicated circuitry, they understand one language that is called action potential. And you might be wondering in the high school book, you might have seen these types of somewhere in the textbook. This is some sketch of neurons, which just a sketch. As you see, this dendrite looks like this types of structure. This is a real neuron. And how does this work? As you see, the action potential is types of a electrical signal that passes through the axons by interchanging those ions. In general, to see, I think that this picture would be helpful. In a in a in a real sense, the axon or the neuron is already in the polarized state. What does that mean? There is a negative potential inside the neurons and the positive potential outside the neuron, because all those sodium and potassium ions are outside and chlorines are inside. So all those neuron cells or our body cells already they are in polarized state. Then when signal or when somebody touches, when you feel something, then when the sensation comes, these channels opens and the ion goes inside and they produce a signal, the spike, what we call action potential. And it also has its interesting feature, it at the certain, when usually the cells are in minus 60 to minus 70 millivolt in the resting potential. When the sodium channels ion opens, this gradually the potential inside decreases. That means potential positive goes start happens, and then at the certain point, these potential sodium channels close, and then chlorine channels open. Potassium channel opens. In such a way, the action potential produces and it passes. And this is a famous Harkin and Ugly equations. You might have seen or not. You can look at those equations, and you can really plot into the MATLAB or in Python to produce this action potential. And the guy, HS or Erskine and Hogley, they got the Nobel Prize on this equation. So I gave you a clear idea now. So far, you get how that neurons work. It's just wondering like how mathematically, how physically, using a physics principle, you can explain its origin of action potential. Now, I'll briefly tell you, it's a very vast subject. I cannot cover everything in detail within this 1 hour talk. I'll give you an overview. So in 2014, we carried out an experiment. As you see, these dendrites, which I had shown here, these dendrites, the network of these Lamopodia or Philopodia, we call them, they sense everything. What we did here is we put a laser spot here, and as you see, the laser spot can turn these neurons in different direction. And so these are the I call them a sensor. Sensor assembly. So the dendrites has so many sensor. Heat, temperature, chemical sensor, physical sensor, anything they can sense. And there is another thing like I carried out the experiment is we carefully calibrated. There is a microelectrode around 1 micron thick, and we culture these neurons in a dish, and we send the current. As you know, when you send the current to the electrode, it produces a heat, and we measure this how those neurons will behave in presence of this heat produced by the electricity. And we carried out this experiment, and we found out these neurons also turns away from that electrode. So heat as well as light, the neurons will sense and they will turn out. This is a graph which is showing how far, at what angle these neurons turns away. And so there is then here is a mathematical calculation. Actually, I did it myself, this math. So what it shows that then what is the reason turning away from that laser, from that heat, what is the reason behind them? Then what we formulate is, as you shine the laser, as you remember that laser absorbed by the medium, raise the temperature, a similar case for the electrode. And that small change in temperature, if you look at that graph D, even a 0.15, even a 1 degree change in temperature, there is a 15% change of probability of opening these ion channels. We call them TRPV1. There is a different channels in those dendrites. One of them is TRPV1, TRPV2, TRPV4. They are TRPV channel, what we call. They are responsible for sensing temperature and heat. So if you change a slightly 1 degree temperature, these channels, this TRPV channel opens, and that's why the neurons will sense. That is just a simulation. So I just give a brief idea how these neurons, work in a nutshell. And another experiment, we carried out, as I will show you here. Mm, in this experiment, what we did, we like to investigate the single cell delivery. I'll show you a movie. From the ultra-fast laser, you can make a very small hole to the cell. Cell itself is a 10 micron. As you see, this laser spot is less than even 5 micron, roughly 1 or 2 micron. So you can make a very safe hole if you optimize your laser parameter. It's not that easy, but if you optimize your laser parameter, you can make a hole. I'll play that video probably. You'll see here. Okay. Did you see that? The hole comes in and goes immediately. It's a very transient hole within a second. So I'll again play here. You'll see here right here. Yeah. So that's why you can make a safe hole in the cell, and you can insert the different drugs and dyes to study like what happens once you send those drugs. This is a mathematical simulation I carried out, like how much size will be happens, what is the physics behind it. We assume that if you focus the laser beam, ultra fast laser beam very tightly, then at the center of the laser beam there is a called plasma formation. That plasma formation vaporize or evaluate the cell membrane layer safely, and that's why these drugs. Then in one of these experiment, we insert that cell impermeable dye. Usually those dyes are cell impermeable. They won't go inside the cell, and you have to kill the cell, fix to the paraformaldehyde. You have to carry out complicated process to stain the cell. In this experiment, we did in the live cell. There is no need to even fix the cell to do the study, because if you fix the cell in paraformaldehyde, you lose the dynamics. And you can see in this cortical neurons, you can even see the connection of one cell. This is one cell. This is another cell before the laser. After the laser lesion, the cells is fluorescence here because the dye that is outside the extracellular medium is going inside, and we can identify its connection. That is one of the also advantage. So the other one, which I'll introduce optogenetics now here. So these cells shows here, there are two types of opsin called channel opsin 2 and these are both the family of microbial opsin. I'll talk to you next slide. These are the protein expressing gene, or the protein expressed in the cell membrane. What we use is we use a laser, same method, that laser, ultra fast laser, to make a hole, and then the gene goes inside and the cell express here. We do this mathematical calculation to verify that protein is expressing in the cell membrane. So that is now I will introduce optogenetics. These opsins, these gene or the protein you are saying fluorescence here are really a opsin. And then study of opsin with light is called optogenetics. Honestly, this is genetics plus optics. Why? Because optics, because these proteins are sensitive to the light. Once you shine the light, they will change their conformation, which is here. So what optogenetics is, in 2005, like scientists from the MIT and Harvard introduced a new idea in neuroscience called optogenetics. This is really a new tool, emerging tool, recently within a past decade. So they found a gene or the protein that is a algae, which is found into the sea water or inside. If you clone that gene and express to the our human body or human cell, they have really interesting character. They are very simple function, on and off. And once you shine the light, blue light usually in this case, channel opsin is excited by blue light. If you shine the blue light, this protein opens. So they act as an ion channel, as I showed into our earlier slide, like as a potassium and calcium. These channels works as the ion channel and also activable by light. That's why it's called optogenetics. And different light spectrum, different wavelength, we can tune around to make them perfect. So once you express those into the neurons or anybody, and once you shine the light, as you see in the without light, they are in closed state. After light, it goes to the conformational change, and then the ion opens, or the channel opens, I would say, and these ions goes inside. So this is the alternative ion channel you can consider. In such a way, you can activate the cell. And this is one of the famous video you can search in YouTube. And the Nature has also called this method of year in 2010. From the Carl Desiro lab, they have used the optical fiber, as you see blue light. This mice has a CSR2 channel of SIN2 in their head, and they can control. And why do we need it? Okay, again, as you see, I'll just give you two examples. There are countless, numerous benefit using or advantage using optogenetics now in neuroscience. One of the example, as you see, if you like to do some brain stimulation, that is usually you need deep brain stimulation or electrical stimulation in some mental disorder like schizophrenia, many mental disorder, scientists use this electric rod to stimulate your brain. And that is painful, invasive. What would be cool if you can do with the light? And in the other scenario, which I'm mostly my research is focused on, I've been working since my PhD. This is a piece of retina. As you see, these are the rod and cone. This cell send the signal to bipolar cell. I'll discuss later much. Most of the disease or the blindness is here due to the loss of this photoreceptor. What that photoreceptor do? They actually absorb light and convert to the electrical signal. What would be nice then if you express those opsin, that channel of SIN2, which I showed earlier slide, if we can express here to any cell, now they will work like as a photoreceptor. Wow, that would be cool. Then the blind person can see in reality. In principle, if you can introduce if you change that light signal to the electrical signal, then that works as a photoreceptor, which is exactly that opsin will do. So let's talk about a little bit first optogenesis, what I did in my PhD and then my first postdoc. I mostly focus on two-photon optogenesis. As you know, optogenesis is in the neuroscience field. Many neuroscientists, mostly biologists, molecular people are working there. As being a physics student or physics side, what I play around is most of that channel of SIN2, CSR2, as many people are using in the neuroscience, is activable by blue light, which falls around 450 on this or 450 to 500 nanometer in this spectrum. What if I do two-photon excitation? If you do two-photon excitation, this blue peak shift to the red, double the two-photon is just to double the wavelength. And what will be the benefit? If you do two-photon, mostly the IR light is less scattered by the tissue, so it can reach deeper to the brain than the single photon. And also, it is safe. IR light is more safe than the blue in the eye also. So there are various reasons that people prefer IR spectrum than the visible spectrum, usually in the medical optics. So what is the benefit? For example, if you use a blue light excitation will excite a lot of the neurons out of the field. But in case of two-photon excitation, you can by there's a noise coming on. I don't know from where. I mean, I don't.
Yeah, just turn on from your side. Just turn on your mic. Kamal.
There you
Kamal,
go. Okay.
you can, yeah.
Yeah. Okay. So that two-photon things, as you see, if you use a single photon, the light will excite all those cells above the focal plane as well as below the focal plane. For example, as you see in this this is a chemistry, some fluorophore molecule. You can see clearly how difference between single photon and two photon. Single photon, it excites all those particles in the beam, but two photon is a very pinpoint, like a confocal, but it's not confocal. This is the nonlinearity of this two-photon system. Only the cells at the focal plane will excite. That also gives, in some of the case, as you know, you like to be more focal, it would be helpful. So two-photon optogenetics has an advantage. It has a deeper penetration as well as spatial localization. You can stimulate cell at single cell layer. And and then usually in the optics field, most of those two photon stimulation or two photon microscope, there is a bulky microscope. People use raster scan, spiral scan, you have to do it. But I did slightly different. We use a multi-mode fiber. As you see in the multi-mode fiber, the single mode has this types of Gaussian profile. But for the multi-mode fiber, it has a number of these modes. They self-interfere each other. And what they produce is, as you see the beam profile of this multi-mode beam, they have a random interference, and some points are very bright, or means there is a very high intensity. That points gives the two photon excitation. That's why I use a two photon fiber optic two photon, what I call FO2PS is a fiber optic two photon excitation. I first show, these are the polystyrene bead. I first show in the polystyrene bead, hey, there is a two photon excitation coming from the fiber. Why not we can use to the cell then? So we use a cell, we transfected to the cell with HEK, this human embryo kidney cell, we transfected those CSR2 and we did the electrophysiology recording, what we call patch clamp. As you see, this is really, I don't know whether anyone is here from electrophysiology background, it's a really painful technique. You have to spend all day setting and doing things. So you attach the electrode to the cell, which itself is a very tricky method, and you record the electrical activity and different current with the different light intensity you can see here. So using fiber optic stimulation. And by that reason, just because I use a fiber, Optics Society of America has chosen this method, that fiber optic 2 method, Optics of the Year in 2013 in medical optics. And they publish this as a yearly volume. They highlight, what is the nice development in 1 year, at least in 2013, that my work has been chosen one of the best work in that medical optics field. And that obviously we can do a lot of this brain stimulation. So far this is a in vitro, right? Then we carried out in vivo also that is also my PhD work. So usually people use blue light, okay? They send the blue light through the fiber, like as you see on my previous image, most of those optogenetics guys use a blue light. We use a two photon combined with the, this beam splitter, as I think many people here are from optics field, that you can combine a different optic element to a beam. And as the shutter opens, we control that beam pulses by shutter, whereas this shutter opens, however the laser pulses, you can see the spike recurring from that electrode, from the mice brain. And that was also transgenic mice, because that mice has already expressing channel rhabdosin 2 in his head. We can buy these mice nowadays, from many labs. So then the advantage of it, as you see, in comparison on 1 mm, 2 mm, 3 mm, we were able to record almost 2 mm. I'll say 3 mm also, but 3 mm is more like, like spurious, whether that is real signal or coming from some artifact. But at least 1 and 2 mm, we can clearly see from that 870 or 850 nanometer, which is double the wavelength, I would say 2 photon, in case of single photon. So what is happening here is we are expressing, these are the transgenic mice, the brain is expressing these light sensitive molecule called opsin, and we use single photon as well as 2 photon, which clearly shows 2 photon reach taper depth. Of course it will do, and it has a that's why we propose that can do more deep tissue stimulation using 2 photon. All right. So also this video, you can see how nice that optogenetics so far. Some cool video. This is orthome, which already expressing one opsin called allurodopsin. There are different types of opsin in optogenetics. Channel opsin, allurodopsin, reach or crimson R. You can study. You can read on the Google. See here. That video. When the line side, it's silence, because there is a silence option there. It goes silence. Now again the mice, you see that light, blue light is there, that mice is blue. And the heart, you see that it's synchronized with that blue light frequency. So the idea is here now, that heart also is using they were expressing that channel opsin 2 there. So in all these cases, these orthome or the mice or the heart, they all already expressing that light sensitive molecule, and you shine by the light. That means you can control, if there is some a different way of controlling, better than any other method. So these are the cool feature of optogenetics. I share you. It gives you a broad spectrum of neuroscience, like how optogenetics is doing. But my focus, as I'm working since couple of years, since I think after my PhD, I joined one postdoc in Kansas City University. After that, I do another postdoc in University of Rochester, which was really a pioneer field in optics already, as well as vision science. So I work there, vision science. Still now I am carrying out. I'm also right now working on the vision science field here in my company too. So let's focus now vision science. Vision science or the visual science is part of neuroscience also. It is a one part. And as you see, the eye, this is our structure of the eye. Most of the lens, this is the cornea. As you see, iris is the color is, the cornea is there. And then the lens, the biological lens, what we call convex lens is there. All these are the small part of the eye. Most of the things, like when the light comes through, enters through the cornea and passes through these lenses and focus to the retina, as you see that tiny arrow here, that small area, that is the real reason, what we call phobia. This small area is all thing for us. Right now, due to the, I believe, since 10, 20 years, we are constantly using bright light, either in the office or outside this white light. So most of our vision is foveal vision. Our eye became useless. Most of those parts are became useless because we don't use dim light. That phobia, that little dim, this is due to that phobia, we are able to read. We are able to identify these small letters. Otherwise, if that phobia, which exists only in the primate, by the way, the phobia exists only the monkey and human. Other animal doesn't have phobia. So, the other animal cannot read the letter. Let's suppose if they were human, if some animal, just a hypothetical question. If by the way, if some animal changes to the very complex feature in the future, but if they don't develop the phobia, they won't read it. So what that phobia has is little dim. That small area, most of the times what we do nowadays, like read, do anything, that is happening here. And this is a OCT picture of the retina passing through the phobia. You can see different layer, like as photoreceptors are the very last. By the way, I works very opposite way. The retina, the light passes all the way up to here, bottom of the retina, where the photoreceptor are. That's why it's, usually some people think God made the eye in the inverted way, but I don't know, like, I don't feel that way. But some people think, why not the photoreceptor at top? Why the light should goes all the way down? Well, there is a logic behind it, but at least, so as you see the retina, the top part is nerve fiber layer, ganglion cell layer, and these are the rod and cone. So these rod and cones are mostly found in the fovea, and these fovea is filled with cone, which are which gives us that high acuity vision, and rod are in periphery. All these outer retina or out of this foveal region, all contains rod, which are responsible to see the dim light. I believe our human ancestors were coming from the jungle when he used to live to the moonlight or dim light when there was no electric light. That times our rod vision would be more activated. And I believe that's the reason that you need that area. But nowadays it must be focusing in fovea. So this is, and this is the sketch. This is the real tissue of the retina. You can see here the photoreceptor at the very bottom. When the light hit, they pass the electrical signal. It passes to the many layers like bipolar cell layer, ganglion cell layer, and a lot of electrical pre-processing happens there. And finally, the signal goes from the optic disc to the brain, and we see the image. So you have to keep in mind that structure in my upcoming talk, at least at the bottom, photoreceptor, bipolar cell, and ganglion cell layer. At least 3 cell layer to get an overall idea. And let's see, okay, what looks like photoreceptor. This is a photo, this is the image of the photoreceptor I took That is a monkey eye, by the way. This is a human eye. Both are same. There is not really difference between these two animal visual system. You might be able to see how many, if you look at the graph, in that center small area phobia, that is the central region, almost 150, 160 million cones per millimeter square are there. That much tightly packed. That's why you can see that higher visual acuity. And this part is foveal region. This part, as you see, this like large bulb-like things are cones, and then smalls are rod. This is out of the fovea. This is foveal region. And the one quick question is, as you see, you might wonder, eye is almost in less than 1 millimeter. So if you roughly calculate the size of the photoreceptor is almost 1.5 micron. And if you invoke that Nyquist frequency, where you need a, the sampling frequency, you need a two times of the frequency, then roughly you need a 2 photoreceptor to see an object, or the least number of photoreceptor you need is 2, which is roughly 3 micron. But our eye cannot see 3 micron. You definitely cannot see 3 micron object in front of your eye. But eye has the capacity, this photoreceptor has that ability to see almost around 3 micron. As I told you, the size of single photoreceptor is roughly 1.5 micron. So use a double it, to use a Nyquist frequency. Why that so? Why is that the reason? Because our eye suffers a lot of optical aberration, lot of error are there, optical, like spherical aberration, higher order astigmatism, defocus. Due to this optical limitation, optical resolution, we cannot see the nicest, like the resolution that eye is built for, or the photoreceptor has. Not only that, the color, for example, if you look at the photoreceptor right now here, these are the cones, and cone has 3 different types of, there are 3 different cones. So in the fovea, foveal is all cone dominated region, that is responsible reading the letters, also perceiving color. That's why in the night, if you go to the shopping to the night in the shopping mall, you might wonder, you will see the different color. Because in the dim light, you can change, you can identify the color. Color only happens to the bright light. So, and remember how we see color. Color is just not the, we usually say, okay, for 50 nanometer is blue. That definitely assign color. Color is an arbitrary thing, I would say, because every photon has its energy. When it goes to the eye, if you think about the like as a detector, whether it is blue or visible, anything.
Kamal, just turn on from your side. Dr. Kamal.
Okay.
Just turn your mic. Turn on.
All right. I think some reason it is muting myself. Anyway. So there are 3 different types of cone. Blue is, we call yes, L, M, N. As you see, blue cone, green cone, and red cone. And there is called rod. Rod is mostly in the 498. So in the night, only the rod activates in the dim light. So we lose the color. But in the day, there are 3 different types of cone. And when it goes to the brain compare the amplitude of the 3 different peaks and determine which is red and which is blue. That is very interesting. That's why, like some boars has 5 cones. They have 5 different cones, and they have spectral properties much more richer than human. For example, boar can see much more color than human do. In other hand, dog has only 2 types of cone, and it does not see a lot of colors as we do. So color is definitely a arbitrary thing that happens only in our brain. And brain compare, by the way, if you are interested, you can read more. But due to the time limitation, I will go a little something. Okay. So the color vision, usually there is a trichometric theory. Probably every people from computer science or any engineering background, you might know. If you mix RGB, you can get any color. So RGB are the fundamental color. So how does it work in our brain? So these are the rod. You see, short wave, medium wave, long wave rod. Cone. You can call blue cone or green cone or red cone. So each cones, there are 3 different types of cone. So when the light falls on, depends upon which, if all cones are activated, you will see blue. I mean, if there is a either of one activated, you will see yellow. It is simply theory of trichometry. You can work on it. That's why people hypothesize. That's why people make a theory about it. Well, sometimes that also does not work. For example, I'll give you an example here. Please focus on that. I'll tell you, focus on that dot for a minute. I'll just for a while, and you'll see what happens. I'll count. Just 1 minute, at least a 30 second, I'll say 30 second, focus on that blue dot only. Do you see that? Some pink color here? You probably, I don't know, it maybe I did a very fast, or you can do
Yes.
later.
Yes,
So
it is.
yeah, after that, this green color, you see the pink, how that is coming up. Because if this trichometry theory is valid, you might see still a green there for a while, but you see the pink. And then people fall in problem, and they are nowadays they are trying to hypothesize, well, there is a complementary pathways because the color does not work like trichometric theory, and people are saying. So still, this is a debate area how the brain works. And so that if you look at the sensitivity of our eye, you might see on this left picture, these lines, you can see our eye, most of our in the daylight, we can clearly see around 10 cycle to 10 to 20 cycle per degree with the very high contrast. But if the contrast works, if you make the contrast low, you won't see these lines. So our spatial sensitivity depends upon contrast, light, different parameters are there, and as well as temporal too. You can see 10 hours, 20 hours easily, but definitely you won't see 50 hours above. Sometimes you might, but that depends a lot of these luminance parameter we have to adjust. These are the basic properties of the vision. Our eye, like it has a sensitivity, spatial sensitivity, it has a temporal sensitivity, it works like as a photoreceptor, but definitely that's not at all. It is really complex, what we call perception. This is a physical example. Let's see this example. Look at, if you try to look at those one white cross section, you'll see dark. This random dot point might be moving here and there. How can you verify this rod? As I showed you earlier, this photoreceptor has a size of 1 micron. They are you can resolve very nicely. But on that picture, if you look at, you randomly see this black dot moving everywhere. That now another problem called perception, you cannot simply explain by this, well, photoreceptor are there, they can resolve. They cannot resolve here. What is the problem? Problem is vision is complex. There is a receptive field. When that signal process from the photoreceptor, as you see, our eye is mostly taking an average. Our eyes try to take the black part. The most of the black area is more than the white. So there is they call on and off. Off cells are there, on cells are there. So when the light, when the dark or the black side falls to the eye, the white off cell activated, and there is a light falls on the other side, the on cell activated, much more complex. My point is, you can simply explain by the vision or our vision just by the photoreceptor density or their size. Similarly here, if you look at A and B, probably you might confuse, well, this looks like what that shape is. But look at here. You probably imagine that is a cube there, right? You see the cube on that 8 balls. Is there really cube? Let's see. That is not cube. Your brain or our brain, it already hypothesizes, it reconstruct the reality. That's why I put a title. We only not see, we create it. Most of the times that happens, the visual cortex, which is higher processing place, is there. For example, here, this is a very famous example in psychophysics. You probably see A and B are different. What do you see here? You know, A looks like more black and B is more white, right? In the chessboard. Is that right? Look at here now. That's not true. What happened? Because I was like fooled by that shadow effect. He thinks that is a, you know, trying to take the average, trying to guess it. You can easily confuse the brain. I mean, not confuse that our vision is not, you know, byproduct of uh, these rods and cones only. There's a lot of perceptions happens in the brain, and that brain reconstructed all the time all those things basis upon the environment. That's why the environment is very important to know what it is. Okay, that's much about vision science. Let's tell you how then we can restore the how we can restore the vision. I think I give you some at least a broad idea about neuroscience and about the our retina, how it works. Forget about how complicated brain is. Brain always relearn it, no problem. Even there is a mess up, any signal going on, if you train the brain, that's why neuroplasticity is coming nowadays. Let's forget about the higher processing in the brain side. Focus about the retina. Most of the blindness, many people, you think people are blind by birth. That's not true. Many people are blind because due to the retinal disease. Most of those photoreceptors will degenerate by AMD, RP. There are many diseases. They damage the photoreceptors. And as you see, when the light comes, the first element are the photoreceptor that changes light to the electrical signal. In physics terms, you can call them as a phototransducer. They lost. How can you restore them? Well, as I said earlier, optogenetics or stem cell, that is the project also I work in my earlier postdoc. Either you put, we are trying to now, you know, it's still not in the, you know, available to the patient now. This is ongoing on the research, still in the bench. Either we are trying to put the stem cell there so that the stem cell eventually convert to the photoreceptor and they will make the connection to the bipolar, and in such a way a patient can see it. That is still infantry, you know, there is no chance, there is a lot of issues. The stem cell does not survive long times. Even if you inject millions of stem cells, there is only one cell survive there. So this is still early phase. In the other hand, the optogenetics, which I've been working since my PhD, what if you express those light sensitive opsin in any cell like ganglion cell or bipolar cell, the more deeper you go would be better. But I work on this layer. So if you transfect those, if you make those ganglion cell light sensitive in other way, let's try to make the other cells phototransductive or in such a way that they can convert light to the electrical signal. And if there is any signal originated, then it will pass to the brain if other circuitry remain intact. And the research shows that usually in those diseases, everything remain intact, only those photoreceptors are lost. These are the circuitry. So, and there is another approach also going, these electronic bionic eyeglasses. That is right now in FDA approved, that is in the market, but it's still, you know, they are, you know, it's not that promising. They have not, patient cannot see anything besides just flash of light. They put a lot of electrode here. As you see, the resolution of the anything comes from the photoreceptor 1.5 micron. How can you make 1.5 micron of electrode of billion number? That's not possible. So even if you put the electrode, it will give a very low types of vision, like only bright and dark things. So ideal would be if you really make that remaining cells or either stem cell or optogenetics make it work rather than putting those electrodes to the eye. The one problem we are facing, like many scientists work on the mice, as you said, mice are good model in many sense, but for the visions, they are horrible. Their vision is completely different. Even mice cannot see the red light. They don't have red cone there. They don't have phobia. So nothing works. If you test something in the mice, that cannot be labeled to the human directly because visual system is entirely different. Any other things like cancer, any other disease, you can use mice model. But the monkey, what we were working in our animal, is very expensive. Only the few lab in the US have that ability to work on monkey because very expensive, need a lot of effort. But the point is, mice has a lot of disease model. You know, they have genetically, you can create that RD model. They can, you can make genetically losing that photoreceptors. But monkey, you don't have that genetic model. People are using chemical. If you put the chemical in the eye, it will messed up everything. So what I did is actually to create that model, I use a femtosecond laser, as I had shown in my previous, that my PhD work, I continued in my postdoc too. You can tightly focus. The problem in my earlier video that I use a microscopic objective, which has high ENA, you can tightly focus the light. But our human lens is horrible. Its ENA is 0.25, where the high objective microscope, you can get 1.33 ENA. Much more tightly you can focus this microscopic object. But in eye, most of the times you have defocus, all those optical aberration happens. Anyway, I calculated using, I model a lot of those parameters basis upon this laser beam scanning systems. You can make tightly focuses like this by taking into consideration these optical parameters. This is axial aspect of the beam. This is a lateral. This is axial. This is a linear. If you think this is single photon, if you think this is a two photon. So two photon or the multi-photon, the nonlinear optics by itself is a very highly focused, very localized. It can create a selective damage. But as I showed how, because eye has very bad optics in the first hand. Second, it has a low ENA of the human lens. But good thing is we have another technique called adaptive optics, which is mostly used in the astronomy. But my professor, David William, is one of the renowned in the field because he used that adaptive optics for the first time to the human eye and shows that nice pictures of photoreceptor I showed earlier wouldn't be possible without this adaptive optics. So anywhere in the overall, if you go to the eye clinic or any other lab who doesn't have that adaptive optics, you cannot see that photoreceptor because that types of resolution only possible if you correct all these optical aberration. That is possible from adaptive optics. As you see, the people, human people eye size is roughly 3 to 4 mm. The higher the size, if you make the bigger the pupil size, definitely diffraction get lesser and lesser. If you make smaller pinhole, as you know, there is a diffraction takes place. But diffraction get better, point spread function becomes nice, but a lot of other higher optical aberration, you know, coma, astigmatism, spherical aberration, all comes into play and make that point spread function bad. And so the adaptive optics can correct. That's why the beauty of adaptive optics can correct, make the very tight focus beam, as well as the pulse laser can control the temperature. So I'll not discuss more about that. And this is the, you know, this is also complicated structure. Only beauty thing is they have a SAC admin wavefront sensor. There is a wavefront sensor which can correct the optical aberration ahead of eye before going to the eye due to that admin segment wave sensor. And as you know, there are a lot of optical elements. The femtosecond laser is there, and if you focus, eye is here. That's why we do the imaging, we do the laser damage. And using this now adaptive optics plus nonlinear optics, remember that adaptive optics help us to tightly make the laser beam diffraction limited laser beam. And the pulse laser, it produces a nonlinear optics. It is highly focal, only the effect happens only focal plane. Second things, the pulse laser, the temperature is fluctuate. It's not like linear. Temperature is much more controlled in pulse laser. So using a lot of technique, you can selectively damage. This is the in-phase view of the different power. As you can see in the OCT layer, this damage is very nice, very clean cut. You can, in this yellow area, as you see, there is a black dot. That means that layer is ablated. That layer is gone, but all of the retinal layers are intact. So that is a very good model now. This part is blind. If you wipe the photoreceptor here, that part of the vision is blind. Now, if you put the opsin or anything here, you can test now whether that person or the patient can see or not. But obviously, this is in macaque, you know, monkey eye. And we carried out histology after, sacrifice the, obviously, I don't like to do, but that is some part of the, research. Sometimes we have to sacrifice the animal. So as you see, this is a real piece of tissue. This part of photoreceptor has gone. These are the photoreceptor, normal side, and this is the lesion side. So that's why this we can further confirm that part of photoreceptor are gone. So our job is now, this part is gone, that part of eye is blind. So we will express those opsins right top of the layer, this ganglion cells layer, and make that eye sensitive to the light, hoping that patient can see in future. And if you look at the photoreceptor, this is a laser beam. As you see, all other photoreceptors are perfect. Only that almost there is almost 100 microns. So if you can, the rough diameter is 100 micron. That much small area is wiped out. Every other thing is intact. And we carried out also functional, whether there is any function. Sometimes, even if you see some bright area, even there is a 1 or 2 photoreceptor left there, it may give you a signal, and we may be fooled by a patient can, or even the data, you may get some artifact. So to rule out everything is gone out, this is a 2-photon fluorescence imaging. These are the intrinsic fluorescence, by the way. You don't have to inject any dye. The 2-photon fluorescence, you see expressing that the very nice way it goes. This is a profile of the functioning photoreceptor. On the damage side, as you see, there is a flat. Therefore, everything is flat here, means none of the photoreceptor exist. We shown that structurally and functionally. Now, beauty part is, this is the tiny hole. As you see, we make a lesion there. So that part is blind, and we put the this opsin, crimson R, in this what we call optogenetics. There are many opsin, by the way, crimson R, channel opsin 2. You express this to the retina. This is a live retina, but that is after the taking GCAM6 image, AO images. As you see, this is a marker for crimson R. We put a fluorescent tag marker, that gene. So that gene is expressing, confirming by that calcium imaging on the eye. So we will see now whether that will see a signal or not. That is our aim. And by the way, the beauty of human eye, as you see, there is a fovea, which is at the center, and these ganglion cell layer are formed as a ring. So you can stimulate in center part. This center part gives the feedback to this ganglion cell. So you can precisely see where you are stimulating and where you are recording. So if you make a blind, if you make a lesion here in this area center part, and if you stimulate here, after putting that opsin, you can identify whether you restore the some function or not. So here you go. This is the recent result. We just published this last month on this monkey. This is the monkey has a lesion. We place the special stimulation, as you see, 2 bars to almost 0.2 hours. This is a moving bar, by the way, on the eye, and no crimson R. With crimson R, that is the one option we put into eye. As you see the signal, so that signal is coming from ganglion cell. So it must be these cells which we now make it photosensitive. Remember that photoreceptor are photosensitive, but they are gone. We evaluated by the light, and we put that light sensitive option to the ganglion cell, which are really responsible to send the signal to the brain. Now we measure that signal by calcium imaging. Hey, there is a signal from the calcium. And as you see, this is a Fourier transform. Then the more the spatial pattern you stimulate, if you change the different pattern of stimulation, you see the different frequency, as well as the spatial pattern. Also, we carried out some image for Fourier transform of this image. We also see this pattern there. So pattern is pattern recognition also a very important part of the vision. As you see, if you see something, you first identify, whether your parent or your son, your relative, how do you know? There is a specific pattern that our brain identify. That's why you know some person is there. This pattern also is appearing on the ganglion cells. So that excited us very much, like, oh, we are really excited. It is not only seeing the signal. Also, it is producing some pattern. That is a very hallmark of that will be a very good thing to restore vision future. And that up to now, this is a ongoing research. Few labs, as I said, few company have started human trial. I myself work with the company. That is the reason I came join to this company. That company also has started a human trial, but it became a part of the company rule and regulation. I cannot disclose anything about this. I know what is going on right now on the thing, but what I can say is not many, few company have started human trial using this stem cell and optogenetic technique. I am very hopeful in future within a 10 year or so, something will be there in the market, but that is very exciting things at the beginning. And since beginning, my research has been highlighted multiple these news media, articles, and APS news meeting. I was also giving their news conference talk due to this some exciting research on my side. And in the conclusion, I don't know how much I put a lot of thing on your head. Just to tell at the brief, retina is really not just a single piece of tissue. It has a sophisticated engineering network you can even imagine. We have no clue yet. We don't understand much of the function, how even retina works. We have some overall idea. Same true through the neuroscience. The brain is very huge, very complex. So many interconnected pathways are there. So many smart engineering physics people we need on this field. And using integrated approach like using advanced imaging, electrophysiology method, or combined approach will definitely. And one thing I forget to mention, nowadays in the US, everywhere is this data science is booming. Data science is one of the #1 job in the US market nowadays. But most of the data scientists work into the biology, by the way, if you know or not, because neuroscience, you need a huge data to manipulate. Human genome is a big project. So most of those data science, or data scientists exist into the, though they are from the physics field, they work on the biology. It would be cool if you have a domain knowledge also. Therefore, those students who are interested to jump to this interdisciplinary research, there is a lot more opportunity to grow there. There are so many things still need to be solved. So definitely, feel free to approach to your professor or even me. If some student have any idea, I'll be helpful always to help anyone who is interested to this field. And definitely, I like to thank my professor Samirendra Mohanty. This is my PhD professor now. He's CEO of Nanoscope company. My earlier postdoc professor David William Bill Milligan, and then my current boss Michael Engels of this company, and all my current that would not be possible without my previous lab workers and co-workers and various funding agency. Of course, I'll take any questions if you have. I don't know whether I rose a lot or what happened.
Okay. Thanks a lot, Dr. Kamal, for delivering really very wonderful talk about the restoring vision to the blind, optogenetics. We definitely got a lot of stuff and learned a lot of things, and you covered almost all the things related with the eyes and the optogenetics and how the vision is we can restore. Thank you very much again. Now I invite Dr. B.D. Srivastava sir to say a few words. Srivastava sir.
Yes, I am here.
Okay, sir.
Yeah.
Yeah, I request you to say a few words about today's.
Okay.
Yeah.
Yes, good afternoon. It was really very nice and enjoyable lecture, very informative, and it was really good presentation. As Dr. Kamal Dhakal is starting from the brain that is the commander in chief, and oh, that is the real good line I
Right.
emphasis. Because of that, the controlling the nervous with light, brain stimulate, the fiber optics. There are several terms which you use really as a physics professor. Uh, some terms I uh, first time I heard that term because I am not very much uh, involved in this opto nervous system
Yeah.
studies. That's why I first time I heard such type of terms. So as far as physics part is concerned, that I understand very well. But the bio part, which you express, is in very nice uh, terms. Uh, the something, the vision restoration approaches is really very good. So I would say that is the very useful lecture, and the fundamental properties, fundamental principles of the optogenetics, they have been presented in a very simplified language. In each subtopics have been rearranged in more coordinated and logical manner by you, and introducing some additional knowledge also whenever it needed. Simple examples have been given to fix up the ideas clearly in the mind of the students, researchers, and uh, myself also. Each subtopic is provided with the problems. That is the very nice and very good. Based on the understanding, knowledge, some numerical calculations also given by you. That is very useful. And the prediction, some predictions also are there. Such type of lecture can be used to extend the solidify the students' knowledge. It is hoped that today's lecture will be useful for UG, PG students, and not only UG, PG students, but the future researcher of the optogenetics subject as a subject. And those who are willing to join such type of subject which involve the physics and the bio both. So this lecture is really very interesting. I thanks a lot Dr. Kamal Dhakal for delivered a nice lecture. Thanks a lot.
It's my pleasure, sir. Thank you.
Thank you very much, sir, to say a few words about the lecture. And it was definitely, no doubt, it was really informative and knowledgeable talk by Dr. Kamal Dhakal. Now I request Dr. Gita Soni to propose a vote of thanks.
Sir, there is one question.
Yeah.
Go ahead.
Hello.
Yes, participants can ask question. Sorry, I forgot to give chance to ask question.
Okay, yeah,
Participants can
feel
ask
free to
question.
ask anything.
Yeah.
Sir, I'm PK Dubey,
Mm-hmm.
and there is some retinal fluid pressure is there,
Mm-hmm.
and
I think your voice is stopping. Jitendra,
Yeah.
I didn't hear anything.
Okay, just wait a minute.
Sir, I didn't.
Okay, sir.
Your voice was dropping.
okay.
Yeah, we can hear you now. Please go ahead.
Sir, some retinal fluid pressure is there,
Mm-hmm.
and
Okay.
it is more than they are using some laser technique to puncture the retina.
For the, I don't know what types of There are two types of pressure, like the one is called anterior chamber in the eye. If you look at on the my
Yes.
slide, if you look at, eye has two big chamber. One is called anterior chamber. There is a one fluid, and this whole hollow, there is called vitreous humor, and a lot of liquid is there is filled with.
Yeah, yeah.
And you are saying if you puncture the retina, does that pressure change or anything else, right?
Ah,
Definitely, you are right. Like if you make a hole, like we are not drilling a hole to puncture the retina. What we are doing is we are making only damage to the small layer. There is a choroid on the bottom of that photoreceptor. If you look at this OCT,
okay.
this is a very thick choroid. You cannot puncture that easily. So
Yeah, yeah.
we are damaging that photoreceptor layer. Many disease damage this photoreceptor. That does not change any pressure or anything. That called intraocular pressure. What we call that. So that intraocular pressure remains. We have a measure it, but that does not significantly change because we are not making hole there.
But doctors are saying that we are puncturing it. We are
Mhm.
making a puncture.
You
Anyway,
are you making puncture? Are you also working similar types of work or?
no, sir. I'm having some. I went to for, some surgeon for general checkup, eye checkup.
Mm-hmm.
He told that you may have some problem, so you should get this treatment. They are having
That
a
is
very
that laser treatment. I believe that is for different types of, they call photocoagulation. If you have some fluid, yeah. Oh, that is a different one. If there is a small fluid in the subretinal space,
yeah,
that
yeah.
is called that is called subretinal space.
Okay.
So there is a laser treatment that called
Laser,
photocoagulation.
laser
That
treatment.
building, that kind of welding kind of thing, and then that also helps. But that is a different pressure called subretinal pressure.
Okay. Thank you, sir.
Mm-hmm. Good.
So
There is one,
one
Dr.
question
Kamal.
from
Yeah,
my side.
there is one question from Ria Soni. If someone has myopia, how can we correct this defect by opto technology?
Yeah, good question. The myopic eye is, there are a lot of, usually, I think in the most of those high school book, even when I was a high school student, we teach, okay, when the lens cannot focus the rays of light at the retina, then either there is a myopia or hypopia. That is not only the reason. The most of the reason for myopic eye is the eye throughout your life, from the childhood, it slightly grows. Its size changes, but the lens focal length kind of fixes in between. Either the lens does not work, or the eyeball size changes gradually. That causes a myopic eye. But the technique what I'm talking here, optogenetics, it does not help for myopic eye because it's not to change the focal length of the lens or the size of the eye. It is nothing to do with. Um, it's just a gene that expressing to the retina, right? There is nothing related with myopic eye, only the focusing problem of the rays of light, not the retina. That can be corrected by either lens, or if you can say, you can use adaptive optics to make it better vision. But the optogenetics, since it is a retinal, the function of the retina, this is with the cell, nothing to with the focus of the light. So optogenetics does not help for myopic or any this uh, hypermyopic vision.
Okay. There is one more question. Is it possible, like heart transplant, can we have eye transplant also?
Great question. Well, I know, yeah, you might
Is
have
there any
heard eye
research going on
transplant.
this area?
Well, eye transplant is there. Many people say eye transplant. If you have paid attention or if you are interested to the vision science, many people donate their eye. But is that real transplant? That's definitely not like a heart transplant where you put somebody else's heart or join the arteries. What does that eye transplant mean? When the person dead, many people has a problem on cornea. this little part, the top part of, if you look at this slide, this white part called cornea. So many people, if the problem is on the cornea, you cannot repair it. Only way you can get the repair is to transplant that cornea. So that's why the eye transplant means once the person dead, they take out the eye and take out that cornea only. Rest of the eye does not work because it is so complicated organ. You cannot transplant like any other part of the organ. I don't think in near future, probably after 100 years, who knows what happens. But because it is so complex organ, too many neuron cells are going to the brain, you can transplant the eye as the heart transplant as we have seen. But in the literature, in the news, you might see people are donating eye or eye transplant. That is only the corneal transplant because eye is very complex. You cannot join those thousands of network or circuitry or those neurons by cutting it.
Okay. Is there any question? Okay, there is a. Okay, how far are we to commercialize the technique that Dr. Kamal presented? How long will it take to commercialize your technique?
Well, it's like many things like stem cell optogenetics, they are in the many right now there is enough data that will give the signal, right? But the vision is so complex. Does that electrical signal reaching to the brain that person will see? We don't know because it's so many things happens. It's not just only the signal going there. Brain do its own adjustment. It makes, as I showed in the earlier picture, brain even recalculate, rethink, it reconstruct everything. But at least the good thing is person will see something, maybe flashes, maybe something, but eventually brain will train to see those images. But how far it will be, we don't know yet. Few company have started in the human trial. It may take 10 years, 20 years, but I expect within a 10 or 20 years to come to
Okay.
the market.
Okay. Participants can turn on their mic. It's open discussion. You can ask question if there is any kind of question rising in your.
What are the hello?
Yes, sir.
What are the pitfalls in applying optogenetics?
One of the problem in optogenetics is definitely, like IR is very sensitive. And many people think that our rod can detect, rod are more sensitive than even cone. Those rods are the one who you can see in the very dim light, like as a moon, even starlight. And there is a hypothesis our rod can measure the single photon. Is it really challenging to measure single photon anywhere? Is it so noisy, yeah, almost impossible like this? But people think
So you were applied two protons.
that is two photon stimulation, right? But
Oh,
we are sending thousands of photon there. We are not doing one photon. Two photon is a process, but in two photon beam there are millions of photon maybe. But
okay.
what is the pitfall you are saying? I understand pitfall means you are saying what is the drawback? One drawback
Yeah.
is the opsin is not that sensitive as our opsin in the eye. You need a lot of light because you can see with our eyes very low light, but here you have to use the laser beam. Whether that laser beam would be really helpful, you put those opsin on the eye and you have to shine by some types of light. That is the drawback. You have to really make it down to the level where even a dim light can stimulate that opsin. Only one challenging many we are facing in optogenetics is it has really high sensitivity, I mean low sensitivity than the actual photoreceptor we have.
Okay. Thank you.
Mhm. Mhm. Any other questions? Okay. Jitendra?
Yeah, there is. Yeah, can you hear me?
Yeah.
there is one question. What other mechanism other than two photon mechanism can be employed to revive the vision in optogenetics?
Well, many people use, two photon we don't use for vision. Two photon I just saw that was used in neuroscience that can penetrate deeper. But in visions, we usually don't use two photon light. Usually, because channel of SIN2, it is blue excitable. We use single photon. Beside then two photon, usually we don't go multi-photon because the higher the photon you go, three photon, four photon is really it's a very rare event. It does not happen all the time. You need to be a lot of things, but there are a lot of other technology like as depermeable mirror, using the depermeable mirror DMD to change the beam pattern. Like splitting the beam in multiplexing the beam, that technology is trying to do is but not going to higher or multi or three photon or two photon, but we need a multiple beams, uh, stimulation pattern like as beam pattern. So much things you can do that makes multiplexing the beam or changing the beam profile of the light, but not definitely two photon or three photon.
Okay. Is there any question? Is there still any question from participants? You can turn on your mic, video, or you can ask your question. Okay, I think there is no question more. Uh, Now I uh, request Dr. Ankita Soni ma'am to propose vote of thanks.
Have a very good one. It's my privilege to post my name to give a bit of thanks to the Dr. Ankita.
Your voice is hold on, ma'am. Sorry, just wait a minute. There is some noise in background. Just turn on your mic and then you can start.
Yes, sir. Can you hear me?
Yeah.
Okay, so first of all, we hope all have a very good morning. It's my privilege to be proposed my name to give vote of thanks. I'm Dr. Ankita Soni, Assistant Professor, on behalf of Government College Manawar. Extend my heartily vote of thanks to the disposed speaker, Dr. Kamal Dhakal sir, from Allergan Eye Care, California, to spare your precious time from a busy schedule to precious work sharing with us. Thank you, sir, for such an informative and interesting lecture. And thanks to the convener and the organizing committee, Dr. Jitendra Solanki sir, Dr. Asst sir, Dr. Anida Sharma madam, and Dr. Bia Srivastava sir for organizing International E-Symposium on Modern Trends in Physics and Biophotonics. I thanks to the audience, organizing committee, and the entire fraternity of the college. I also thanks to the principal sir, Dr. R.C. Pantel sir. I thank you all for being with us this time. It has been a great pleasure once again. Thanks to all. Thank you, sir.
Thank you, madam, for giving vote of thanks. Thanks again, Dr. Kamal Dhakal, for delivering wonderful and informative and knowledgeable talk. Once again, I thank you from the IAPT and from IQAC, from Department of Physics, Government College Manawar. Thank you very much for accepting our invitation for delivering this talk. Thank you very much.
All right, thank you, and it's my really pleasure to speak all of you, including faculty and student there. Feel free to shoot me an email if you have any interest or questions regarding this research or field anything.
Mm-hmm.
And once again, thank you for providing me this opportunity to share my work with you. Thank you.
Thank you. Thanks. Thanks to all the participants for joining us. Thank you very much. श्रीवास्तव सर एंड कर दें?
Good night from here.
Okay. Good night. Good night. It is morning here. Good night.
Okay.
Okay. Have a good night. See you.
You too. Bye.
Bye.